Hey friends, welcome to my channel, and in this video I am going to discuss a very important topic, a particular reagent which is called red Al. This is a hydride source of aluminium. You know about LH, but this is another derivative of LH. So basically it reduced a alkyne to a alkene, but the reaction is regioselective, that is you will get regioselectively the trans alkene. So let's start today's topic. So red Al is basically this reagent. Aluminium, you have two hydride here, and here you have this group which is called 2-ethoxy-methoxy group. You can see this is OMe group, so this is methoxy and this is eth, means two carbon atoms, so it is called 2-etho. In this case you can number it 1 2, so it is called 2-methoxy-ethoxy group. So this is basically called red Al, and full form here you have a minus, so sodium generally is the counter cation, so it is called sodium 2-ethox sodium bis 2-ethoxy-methoxy aluminium hydride. So this reagent is very important in reducing alkynes, okay, and it gives a particular regioselectivity. So let's say you have an alkyne like this where you have a Si-Me3 group, and this is your alkyne. Now here you have a OH group, okay. So when you react it with this red Al, what product you will get? You will get this trans alkene, okay. So regioselectively you can reduce this double bond to trans. Now you know that trans alkene can be obtained from also the Birch reduction, but this is another reagent red Al which will give you regioselective reduction of triple bond, that is alkyne. Now the question is, what is the mechanism? How a hydride source, that is like, or LH, if you use LH also, and if you have this OH group here, so the main factor is the presence of this OH group here. So instead of red Al you can use LH also, but red Al is the specialized reagent for this particular reaction. So now the question is how the reaction is occurring. So red Al is basically the aluminium hydride. So first what will happen, this OH will coordinate with aluminium, so it will form like this. So first of all you have OH here. Now this is L H2 and this is 2R group, I can write OR2, so here you have a minus. Now this hydride will take this, so you have negative charge on here, that means you have a negative charge on here, and here you have LHOR2, so this negative charge will coordinate with L. So first you will get this, so here you have Si-Me3, now you have O L, and here you have hydrogen or now again a negative charge comes on here. Now next what will happen? So next thing what can happen is that this negative charge, this hydride can take another hydrogen from other, so you have other molecule present in the reaction medium. Let's say this, sorry, here you have, will have one carbon like this, Si-Me3. So this hydride can again take one hydrogen from here. So basically in this step this negative charge gone on the aluminium, so it is now capable of accepting another electron density. So next what can happen, this triple bond coordinate with this aluminium, so you have this type of coordination with aluminium with this triple bond. Now another molecule of this red Al which doesn't react yet, or which reacted but where aluminium has a negative charge, that can come closer to it. So here you will have 3 OR group, because 2 from this and another from this, or you can have 2 OR and 1 hydrogen also. Basically you will have a tetra coordinated aluminium, and then this is a hydride source. Now this hydride will attack on this carbon atom, okay. So if it attack on this carbon atom, this bond will go here, So you will get this type of, so here I can write, so you will get a 1 2 3 4 5. So a 5 coordinated intermediate you will get like this. Okay, so here you have this, and now you have a silicon SiMe3 group here, and here you have OR group. Here you have negative charge. Now you can see this particular intermediate you are getting. So after that, when you quench this intermediate with uh, acid source, that is H plus H2O, what you will get? This bond or this Cl bond, which will be protonated. So in this case you will get a protonation here. So you can see you will get SiMe3, actually SiMe3, and here you will have this OH group. So you can see due to the formation of this particular 5-membered intermediate from here, it gives this trans stereochemistry. So why this attack is occurring here? One reason is that it will form this 5-membered intermediate which is stable than 4-membered one, and you can, if you consider this as stepwise manner, so in this step a negative charge will be generated here. So basically I can represent it like this way also, Al OR whole twice O, and here you can see if you consider a negative charge here, so you know this silicon can stabilize this negative charge, although it will form in the sp2 hybrid, but initially it will be in the p orbital. After formation it will go into sp2 orbital. That cannot be stabilized with silicon, because that will be also, but silicon has d orbital. Okay, so it can also stabilize. Basically whenever you have a negative charge adjacent to silicon, it can stabilize, it can be stabilized by silicon atom. And also due to the formation of this 5-member type intermediate, this reaction is favored in this particular pathway, so that will give you this trans double bond. So this reagent is very important, and if instead of silicon here you have, let's say, CO2 or ester group, then also the reaction works, and the reaction is also fine with LH. So this radal is a very important reagent. If you don't know what is the role of this reagent, you will be confused in the exam. So I discuss this with you, and if you like the video, then give thumbs up, and thank you for watching, and best of wishes for the upcoming csir-net exam.